Hey, and welcome to another amazing day of chemistry with Chem Coach Powers. I am so glad that you have decided to join me today on this adventure into electron configurations. So, electron configurations. I'm going to tell you that this topic sometimes befuddles a few students, and they're like, whoa, what's the point? The point is that every single electron has a unique position in the atom. And what we want to do is we want to teach you how to figure out the filling order so that you can understand that the position matters. For instance, I talked to you a little bit before about magnetism. The reason that some materials are magnetic is because of the way that their electrons are configured. So we're going to talk about electron configuration. We're going to tell you how to look at the periodic table, choose an element, and figure out what the electrons are looking like there. And those arrangements can tell us a lot about things like magnetism, other things as well, things like its reactivity. And understanding, hey, this little arrow is right here on this little line. It might not seem to make that big of a difference, but in reality, it can tell you a whole lot about that one particular atom if you know what that one particular arrow on that one particular line is doing. Okay, so we're going to dive into the electron configuration, and you're going to understand more about the atom than you ever thought you would, and it's really going to be cool. All right. So electron configurations, our objectives here today are to be able to write electron configurations and orbital notations. And then we're going to identify valence electrons in the electron configuration. And again, those valence electrons are the ones that are really important because they tell you about the reactivity of the element. And then you're going to show, okay, your criteria for success. You will be successful when you can show electron arrangements, and you should be able to do it using both orbital notation and electron configuration. And again, we're going to look at the valence electrons. You should be able to explain that those valence electrons are the atomless electrons, and that they are the ones that are going to identify certain characteristic reactivities, the properties, and that you'll then be able to figure out which ones in an electron configuration are valence electrons, okay? So what kind of rules do electrons follow? They follow a couple different rules. We have some fancy names for them, and we have some silly names for them, okay? So you should probably know the fancy name. I'm not going to ask you the silly name on the test, but the silly names are going to help you to remember what these are doing. So the Aufbau principle says that electrons fill orbitals one at a time, starting with the lowest. This is kind of, we call this the lazy tenant rule or the lazy pig rule. As far as the lazy tenant is concerned, imagine that you just got into a New York City high-rise, okay? You're about ready to live the life in New York. And so the landlord accepted you as a tenant, but then he says, okay, listen, I know you're about to move in. I have got a floor, and that floor is on, I've got an apartment, and that apartment's on the first floor, or the apartment's on the 7th floor. I'm sorry, our elevator doesn't work. Which would you like? And you're thinking to yourself, let's see, do I want to walk up 7 flights of stairs a couple times a day? Because remember, in New York, you go to the grocery store every day for the most part. You don't just shop once a week. You just got to go get your dinner, and then you come back. So you're thinking about that, and you got to go to work, and you're back, and you got to go down to the park and walk your dog and back. And you're like, yeah, I'll take the first floor, thank you. And that's the Aufbau principle, okay? Also, we can talk about it in terms of pigs. We've got this little pig story that we're going to come up with. And pigs are lazy. They're not going to want to go into a pen that's far away. They're going to want to choose the closest pen they can. They're going to find that close pen before they go to a far pen, okay? So that's the Aufbau principle. Pauli exclusion principle. This one basically says that the pigs will never face each other. Or if we're talking about just electrons, that they must have opposite spins, okay? His principle basically says that no two electrons in an atom have the same quantum address. They must be opposite spins. I talked about that at the last lecture. And so here's what that idea is like with the terms of our pigs. If two pigs are going to be in the same pen, they're not going to face each other. Okay, they're going to be like, They're going to be like this. Like, I'm going to look at your butt. You're going to look at my butt, but I'm not going to look at your face. Your face is uglier than your butt. I don't know. Maybe that's true with pigs. I have no idea. I don't think so personally, but I don't know what pigs think. Okay, the next one. And we're going off on a tangent. Hund's rule. Okay, now this is the empty bus seat rule, or the pigs hate each other rule. And this is the idea that the electrons have got to make sure that they are going to always go into different orbitals if they are going to be in the same energy level. Okay, so the way I like to think about it is, if you guys have ever ridden a public bus or a public transportation, train, whatever, and if you've done it by yourself, you get onto the bus and you look around, the first thing you're looking for is, where's the empty seat? And you will find the empty seat and sit there before you're going to choose somebody to sit next to, because you don't know these people. And then some of them kind of look a little scary and, all that kind of stuff. So it's the empty bus seat rule. Now, if there are no other open seats, then you're going to share, but you're not going to share until there's no other seats that are completely empty. And that's the idea here. Same thing with the pigs. Pigs are not going to share a pen if they don't have to. They're going to go and they're going to find an empty pen. As long as it's in the same area, they're going to find the empty pen and go into that. If they have to go up a level, then forget that, right? Maybe I guess I'll share, because they're more lazy than they are hateful, okay, these pigs. So anyway, these are your three different principles. Those different scientists are named after. You don't have to know the scientists per se, but you probably want to be familiar with the name of the rule. So Aufbau, Pauli, and Hund's. Okay, so let's talk about two different ways to represent what our arrangement is for our electrons. One is with an orbital diagram, okay? Every single little box, or sometimes we can use a line, all right? If we want to use a line instead of a box, we can do that. Here's a little line, okay? Those are orbitals. Every box or every line is representing an orbital. Remember, you can only fit 2 electrons in any one particular orbital, right? And what we're going to do is we're going to then draw the arrows inside these little boxes with these little lines. So if I were looking at carbon and I wanted to represent the way that electrons fill carbon, I would draw little arrows. Now, I do a one-sided arrow instead of an arrow that has 2 parts to the head. And the reason I do that is because it's just easier, okay? You get the idea, and yeah, it's a little bit easier. And so this is how they would fill up, okay? And I'm just going to show you, what it looks like. And if this is carbon, we won't even have that last one there. Okay, so this is called an orbital diagram or orbital notation. Okay, orbital diagram or orbital notation is what we're showing here. And again, I might just have lines. Now you'll notice that there's one line for my S sublevels, and then for my P sublevel, I have 3 lines. Because remember, in the P sublevel, you have 3 orbitals. Okay, in the S sublevel, you only have 1 orbital, right? And so, so that's what that looks like, okay? Now, there's a particular filling order. We're going to talk about that. We're going to learn about that filling order. And before we do that, we're going to show you what electron configuration is. So electron configuration basically takes that same setup and puts it into these little symbols of numbers and letters and little exponents or superscripts, okay? Now the numbers are the energy level, first energy level, second energy level. The letters are the sublevels, S, okay, and P. And then the superscripts are the electrons. So I've got 2 electrons in my 1s sublevel. Here we go. 2 electrons in my 1s sublevel. 2 electrons in my 2s sublevel. 2 electrons in my 2p sublevel, okay? And so this is the electron configuration for that orbital notation. That make sense? Okay, so let's look at this diagram. Now this diagram is going to kind of show you how each element would have a unique electron configuration, or in this case, we're showing the orbital notation. Each element would have an orbital notation that's showing the energy levels. Now notice I have the energy over here, and it's going up. So it takes the least amount of energy to put an electron in my 1s, okay, sublevel. So here's a 1 electron. Hydrogen has 1 electron, and so it looks like that, an up arrow. If I go to helium, okay, there's the electron. There's the electron configuration. Come back to that. There's the electron configuration, 1s1. That's the electron configuration of hydrogen. If I go to helium, which has 2 electrons, then I'm going to fill 1 more electron in here. Okay, but now it's got to be a down arrow, right? Because my pigs don't want to face each other. So if they're going to share the same pen, then they're going to face in opposite directions. But he's not going to go all the way up here because he's lazy. There's too much energy to go all the way up here. Again, more energy to get up to the second energy level, right? And so this is my electron configuration for helium, 1s2. Okay, so now let's look at lithium. Lithium has 3 electrons. I can't fit any more pigs in there. Okay, no more electrons will fit in a single orbital. So it's got to go up to the 2s sublevel. And so my electron configuration is now 1s2, 2s1. If I want to talk about beryllium, I've got to add another electron. And so I've added my electron facing in opposite direction. He can't go over here. This pig can't fill into this one because this is a whole different bus, okay? This is a whole different level of the pen. He doesn't want to climb up those stairs to get to this next pen. He wants to stay here and just face the other guy's butt because that's more convenient than trying to go up some stairs, right? So his electron configuration is 1s2, 2s2, okay? 1s2, 2s2. And now if I want to go to boron, now I can't fit any more pigs in there, so I'm going to have to go up the stairs. I don't want to, but I gotta. And so he goes up the stairs and he faces this direction. Another pig comes down and he's like, oh, no, that's filled. Oh, that's filled. Okay, now I'm going to have to go to the next one. Now, boron's electron configuration is 1s2, 2s2, 2p1. If I go to carbon, I've got 6 electrons, so now this pig has to finally come up into this little guy here. Oops. Now, the question is, does he go here? Or does he go here? Okay, we know he has to go to this level. He has to go up the stairs. But as long as he's on the same floor, does he want to go to this one? Or does he want to go to that one? Remember, pigs hate each other, right? So they're not going to share a pen if they don't have to. So he's going to come over here. And so this is the configuration you would have had. And it would have been 1s2, 2s2, 2p2 as your final electron configuration for that. Okay? So how do you figure out a configuration or the notation on your own? Well, we're going to look at the periodic table. The periodic table is going to give us all the hints we need, okay? So, first of all, we understand the order of filling, okay? We understand that they've got to fill a particular order. Now, the periodic table actually tells us that filling order, and it's an amazing thing if we just follow along the periodic table. But we can also come along, and I can show you a little diagram, a little mnemonic diagram that will help you to figure it out, okay? And some other different things that you might be able to do as well. The thing you have to remember, though, is that orbital numbers, right? S has 1 orbital, P has 3 orbitals, D has 5 orbitals, and F has 7 orbitals. And you have to remember that 2 electrons only, that's a max, can fit into each orbital. Okay, so first energy level, second, third, fourth. Now, again, how am I going to know that I go from 3P and all of a sudden I do 4S and then I go back to 3D? Well, it's kind of crazy, right? Well, if you look at the periodic table, it's not so crazy. So let me bring on periodic table real quick. Hopefully this one is one that you can see. The other one I was showing you was kind of shiny. It was a little harder to see. Now, if you will look at this periodic table, you can follow through and just go left to right on the periodic table from row to row, and you're going to be able to see the filling order. 1s2, okay, those hydrogen helium. 2s2, where do you go next? Just go left to right. 2p6. These are the P's. These 6 columns here are P's. These 2 columns here are S's. These 10 columns here are D's. These columns down here, 14 of them, they're, 7 of them, they are the F's, okay? 10 and 14. 1 for each electron, 7 different orbitals, right? So there's 7 orbitals here, and there's 5 orbitals here, but there's 14 electrons down here, 10 electrons here. So anyway, we hit our 2p. Now we go to 3s. What's our next thing? Oh, 3p. Now we go 4s. Oh, what do we hit? We can't go all the way over here yet. We have to go through 3d, and then 4p, and then 5s, and then, oh my goodness. So what we're doing is we're starting to figure out that the filling order is actually present on our periodic table. The thing you have to remember is that this little level right here is 1 less, okay? This level down here, the F's are 2 less than the energy level. So once I hit my D sublevel, this is where all my D sublevel electrons are, I've got 1 less than my energy level. So if I'm on my 4th energy level, this is my 3rd D sublevel. Everything is 1 less for the D's and then 2 less for the F's. All right, so I have now got a little picture here, but I'm going to show you a little mnemonic device that's going to help you to follow this out. If you will just write down, it's called the diagonal rule, if you'll just write down all of your energy levels and your sublevels in this order, put all your S's together like this, 1s, 2s, 3s, 4s, 5s, 6s, 7s. You do all your P's like that. Okay, now your P's are following, right? 2s and then 2p. There's no such thing as a 2d, so then we go on to our next one. 3s, 3p, 3d. No such thing as a 3f. 4s, 4p, 4d, 4f. And you basically do this, and then you draw the little arrows, and you follow 1s, 2s, 2p, 3s, next one's 3p, 4s, next one's 3d, 4p, 5s, and you just follow along, and you can figure out the filling order, okay? So there's lots of different ways you can do it. Periodic table is great. This little mnemonic device is great. Maybe you can just memorize it. That's fine. But figure out a way to know the order so that you can write down an electron configuration, because if not, you're going to be in trouble. Just remember, the amount of energy is what we're showing. And so these are the amounts of energy that are present in each of these different energy levels, okay? And so it takes less energy to fill up 4s than it does to fill up 3d. Now, there's some reasons for that, but we don't go into those reasons at this point. We're like, that seems crazy. Yeah, it kind of does. But remember that 3d sublevel has got some really crazy, complicated orbitals, right? The cloverleaf stuff. And so it ends up taking less energy to just throw yourself up into a 4s than it does to fill up, a 3d. All right. So what would the complete electron configuration be for calcium? So I'm going to pause it, or you're going to pause it, and practice. Go. And we're back. And so what would that configuration be? Well, you should have had 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Okay, that's the configuration for calcium. All right, there's another thing that we can do, because that gets long, especially if you're doing some of those elements way down the periodic table. They're really long to write out the electron configuration. So we have shorthand, a shortcut way of doing it. It's called the noble gas configuration. And basically, we just need to take the noble gas that is above and to the far right. Okay, so whichever element, if I were doing iridium, I would go up and I'd go over to the far right and I'd start with xenon. Okay, you're going to take the noble gas that's up and to the far right, and you're going to start with that to write your noble gas configuration. It makes it a lot easier because you can skip everything that was ahead. Now, the reason I'm doing that, and the reason I can do that, is because xenon has a particular electron configuration. So if I say, hey, xenon plus whatever follows will be my iridium, then it's the same thing, because xenon's configuration is going to be the same as iridium's beginning configuration. All right, so symbol for the previous noble gas or group 18 elements is put in brackets, and then the electron configuration is written from there. So for instance, sodium, which we might normally write out as 1s2, 2s2, 2p6, 3s1, we go up and to the right, and we see that neon is the noble gas that's up and to the right from sodium. And we say, okay, well, we start with neon, put that in brackets, and then we just finish off with what's in the rest of that column. So in the rest of, in the rest of row 3, or energy level 3, I've got the third energy level, and then the S sublevel, one electron. Mg, magnesium, would be 3s2. Okay, and so you're just writing what you have left over. Neon plus 3s1 is all you've got. Okay, and so now you know neon is going to be that, and so you could write out your whole electron configuration if you wanted to, but you don't need to. All right, so now you're going to practice. Write the noble gas configuration for sulfur. Pause it and practice, and you're back. And your answer should have been neon plus 3s2 and a 3p4. Okay, that is the noble gas configuration, or the shorthand configuration for sulfur. All right. So if we ask for a complete electron configuration, we want the whole thing, a long one. If we ask for noble gas configuration or noble gas notation, that means you can use the shortcut. But pay attention on the test whether we ask for the complete electron configuration or the noble gas configuration. If we just say electron configuration, we probably want the whole thing, okay? But if we say noble gas configuration, then you can give us the shortcut. All right, so now let's talk about valence electrons. Remember that these are the most important electrons because these are the electrons that are actually present in reacting with other elements, okay? These electrons are going to be the ones that determine the atom's properties of reactivity. Okay. Now, the protons are determine the properties, and other types of properties with regard to the elemental properties, but the reactivity properties, they are determined by these valence electrons. They're the outermost or highest energy level electrons, and they're always going to be the ones that are S and P. So I say highest energy level, but they don't include D's or F's. Always include just the S's and P's, because those are going to be the highest energy levels each time. Nitrogen, for instance, 1s2, 2s2, 2p3. Well, which ones are my highest energy levels? Well, I've got my 2s, right? Second energy level, that's the highest energy level, SPs. Pay attention to the highest energy level, SPs. And how many electrons do I have? Oh, well, I've got 2 electrons and I've got 3 electrons, which means my number of valence electrons is 2 plus 3, which is equal to 5, okay? So I've got 5 valence electrons in nitrogen. Now, if you look at the column, number for nitrogen, you'll see it says 15. Well, that 5 in 15 tells you how many valence electrons. Column 14, 4 valence electrons, okay? It doesn't include F, don't include F. 17, 7 valence electrons. 18, 8 valence electrons. Those little columns can tell you how many valence electrons they have. Now, that does not work for the D sublevel or the F sublevel, but it does work for S and P sublevels. All right, so nitrogen has 5 valence electrons. And again, you can look at the periodic table, look at the column, and you can figure out the valence electrons. But again, only for the S's and only for the P's. That does not work for the D's or the F's, okay? All right. Now, there you go, okay? So again, 1 valence electron, 2 valence electrons, 3, 4, 5, 6, 7, 8 valence electrons. It's going to be different in here, all right? So don't use it for that. Okay, so let's try it out. You're going to practice and then come back. Ready? Practice it. Pause it. Practice. Pause it. Practice. You're done. You're back. Okay. Fluorine. How many valence electrons? Well, you look over there and it's in column 17, which means it has 7 valence electrons. Rubidium, Rb. You look on the periodic table. You're like, oh my goodness, where's rubidium? It's all the way on the far left. It's number 37. And so it's got 1 valence electron. Sodium is number 11, also first column, 1 valence electron. Carbon, it's in group 14. It's got 4 valence electrons, right? Which are the valence electrons in this configuration? Well, I got to look at the highest level S's and P's. Oh, here's my highest level, 4, and I look at my S's, therefore my answer is 2. Okay, 4s2. So which element is this? Go to the 4th energy level. 4th energy level, 1, 2, 3, 4. And then I've got to go 2 over, 1, 2. That's calcium. Boom, you're done, right? So knowing what the electron configuration is can tell you which element you're dealing with, and it tells you about its reactivity. See, every single one of these is super reactive, and these are pretty reactive, and these are really reactive, and these are not that reactive. Like, each one of them has certain reactivity characteristics based on the number of valence electrons. Now, we'll learn why that number of valence electrons affects its reactivity so much later on. But just know for now that it does, and that you can get a little bit of extra information if you're looking at those. Okay, so pause it and practice. Again, this is your exit ticket. Can you write the electron configuration for helium? Write the orbital notation for boron? How many valence electrons in an atom of carbon? And the noble gas configuration for chromium. And you're out and you're back. Wow, you've been gone so long. Let's look at what those are. All right. So configuration for helium. You just have 1s2. Boom, done. Easy, right? Orbital notation for boron. I've got to do my little lines. 1s, 2s. It's got to fill up my 1s first, up and down arrow, and then I've got to go to boron, and boron just has one more. We always start with the up arrow. Does it really matter? We don't know which way it's actually spinning, so in some ways, no, but we always start with the up arrow. That's our convention. And then we go, and we got to fill that one out. Boron's number 5 on the periodic table. So then we got to figure out one more electron. Got to fill up those 2 plus one more. So this is the orbital notation for boron. How many valence electrons in an atom of carbon? You've got 4 valence electrons in the atom of carbon. It's in that 14th column. That's going to tell you it has 4. Write the noble gas configuration for chromium. All right? And so chromium, oh my goodness, this is going to take a little bit longer. Wait, but it's noble gas. That means there's a shortcut. So I look at chromium, it's number 24, right? And so I go up and over. I can start with argon. Sweet, that's going to be easy. I get to start with argon. And now I just have to write in the rest. And I just say, oh, 4s2. 3D, 1, 2, 3, 4. Okay, 4s2, 3d4. Now, I will tell you that there are some exceptions, and if you look in the book, there's some exceptions with column number 6, chromium, molybdenum, tungsten, that kind of stuff, and there's some exceptions with column number 11. We're not going to have to learn those this year because we're taking a kind of a little bit of a shortcut because of the whole online learning thing. But here, let me show you what actually would happen. It's kind of silly, but what happens for chromium, the real answer for chromium is actually 4s1, 3d5. Let me show you why. Because here's 4s, and here's our 3d. Remember that 3d had 5 different orbitals, right? And so we were like this, and we were like 1, 2, 3, 4. Well, for some reason, chromium, it don't like that, okay? It doesn't like having this one last little empty orbital. And so it steals an electron from 4s, is that root or what? And it puts it into its 3D. Okay, same thing for copper. Copper does that same thing. So basically column 6, column 11, they do the stealing thing. It's really interesting. So anyway, that's what they do. You don't have to know that for this test. Some tests, you know, most years we make you guys know what the exceptions are. You're not going to have to know that exception, but this does make a difference. This right here makes chromium pretty magnetic. Okay. Remember we talked about, you know, having certain things being magnetic. And so certain things are more magnetic when they have electrons filling in one of those, you know, particular electrons. So this is one of those that has magnetic properties. And that's one of the reasons is because it has 5 empty or 5 half-filled orbitals that are all having electrons spinning in the exact same direction. And so chromium is one of the elements that they use in magnets. So yeah, pretty cool stuff. All right, let's see what we know. Can we go over these objectives? I bet we can. All right, so write electron configurations, orbital rotations. Yeah, we did that. Identify valence electrons in an electron configuration. Okay, yeah, we did that. Can we now do this ourselves? Can we show electron arrangements using orbital rotation, electron configuration? Yeah, we can now do the little boxes or lines, the little numbers underneath it. And we can also do the 1s2, 2s2 stuff. Yep. Figure that out for our elements. And then we can explain valence electrons, or the last electrons, the outermost filling electrons in an energy level, and that they have to do with reactivity, and that again, you just look for the highest level S's and P's. Now, this is pretty easy stuff in some ways, but some students kind of feel like it's a little complicated too because it's a little bit abstract, kind of the same thing like that quantum numbers were last time. So if you're having trouble with this, you know, make sure to drop me a comment and ask me a question. Yeah, come in and ask me a question or ask me a question online, and I'll definitely be glad to help you out with this stuff. You now can understand that the arrangement or the configuration of electrons actually has a lot to do with how atoms behave. And that's why we learn this stuff, because if we can understand that their arrangement affects their behavior, then we can understand the atoms so much better. I hope you enjoyed this lecture. I hope you enjoyed learning more about the intricacies of the atom and electron configuration. I hope you have an awesome day. Be kind to one another, and God bless you.